what we have here is a telescoping sum. It's finite, and the equation amounts to 2025. If you could look at the left-hand side, we have that we have a pattern here. We start with the value of 1, subtract 2, add 3, subtract 4, and so on. And then we add n minus 2, subtract n minus 1, and we terminate this partial sum at the value of n. And we want to figure out what this value of n is, given that the left-hand side equals 2025. So, as I will show, the value on the right-hand side here, 2025, is, it's not, I guess, it's not necessary to have the right-hand side equaling that value. Depending on what that value is, we'll just adjust the value of n. But for whatever reason, I've chosen for it to be 2025. So we have this sum, and I want to simplify it somehow so that I can form a simpler equation to be able to solve for the value of n. Right? The key to do this is to identify a pattern within the pattern, and usually with these kinds of sums, we want to pair them up in such a way, and then, or in this way, simplify the expression. But how do we pair these terms exactly? Okay, so what we have here, I should mention that at the end of this this series, we're adding the value of n. Right? So we're subtracting something, and then finally, we're adding something to give 2025. Right? So you should notice that every time we subtract a number, that number is going to be an even number, 2, 4, 6, which means that this value here of n minus 1 is going to be even. Right? So let's pair the terms in this way, because if we do so, we can notice that when we have 1 minus 2, that evaluates to negative 1. Pair these terms, we get negative 1, negative 1, and so on. And then if we pair these two terms, the third last and second last terms, that will give us negative 1 as well, because we know the pattern continues, but at the end, we add the value of n. Okay. So the question you should be asking is, how many times are we subtracting negative 1? If we know that, it should be easy to figure out what we have to then add to give 2025. So I'm alluding to forming some sort of algebraic expression in order to solve for this value of n. Right? So let's go through the pattern. So let's look at the even numbers. So when we subtract 2, the sum at this point is negative 1. Once we subtract 4, the sum at that point is negative 2. When we subtract 6, the sum at that point is negative 3. So you're adding these terms here. Right? So the pattern continues. Right? So let's say the 2, the sum is 1. When you subtract 4, the sum is, negative 1, negative 2, up to numbers. So this is kind of informal notation here. When you're at 6, you have -3. When you're at n minus 1, right, what is the sum up to that point? Well, if we look at the pattern here, we're dividing by 2 each time, right? So at n minus 1, the sum should be negative, whatever n minus 1 is, divided by 2. So that's key to simplifying this left-hand side. So let's cut that. So let's simplify. So we have the left-hand side, and that would equal, so up until this term, we have, as I've just shown, we have a negative value, n minus 1 over 2. Right? And we still have to add the value of n, and that gives us 2025. So we've turned this telescoping sum into an algebraic equation we can then quite easily solve. So this is the, I guess, easy bit. Let's expand. We have minus n on 2 plus a half plus n. 25. So we have n minus half of n, giving us half of n plus a half, 2025. Multiplying both sides of this equation by 2 gives us 4050, forcing n to be the value of 4049. So that's the value of n here. So as I mentioned, there's nothing special about this value here. Depending on what the value on the right hand side is, just adjusts this, forcing n to be just some other value. Right? So we have this series here. It was important to identify what the pattern was and then simplify it so that we can we know what the value of n is to make this equation hold. And there you have it.